Hi everyone, my name is Farid and today we're gonna talk about digital electronics and the main topic is combination logic using multiplexers. Actually, this is my university project, so we have the book that you see on the screen, Digital Fundamentals by Floyd. I would supply you with the link in the description, so the Amazon link. And from this book, I got the experiment number 12, combinational logic using multiplexer. There is a main task and two application of multiplexers that I voluntarily did. So the first one is constructing a 2-bit comparator using 8-to-1 multiplexer. It could seem somehow complex for you, but I will explain what a multiplexer is and what's the main task here. The additional tasks are constructing parity generator with 8-to-1 multiplexer, and finally constructing BCD invalid code detector with 8-to-1 multiplexer. So let's go on. Firstly, let's see what is that so-called combinational logic. In digital electronics, there are two main types of logic. So combinational logic and sequential logic. In combinational logic, the output accounts for a set of Boolean expressions defined by the input. So if you use the combinational logic, you would have the Boolean expression for that logic and you would see what would be the output if we give that inputs, if we supply that inputs. However, in sequential logic, the case is not like that. The output also depends on the previous states of the input. So let's say the output is 0 and it becomes 1 because the input state is 0, but the input state before that was 1. But if the input state before that case was maybe 0, the output would be different. So it can be also phrased as the sequential logic has a kind of memory. Many circuits used in computers such as half adders, full adders, half subtractors, full subtractors, multiplexer, demultiplexer, encoders and decoders are made by using combinational logic. But what is a multiplexer? So multiplexer, in other words a data selector, is a device used to route the desired input signal among many other signals to the output of the devices using the selector pins. So basically here you can see a diagram for the multiplexer. We have 3 selection pins and 7 inputs, and we have 1 output. So multiplexer choose 1 input and routes it to the output. And what helps to do that? These 3 selection pins. So that's why it's also called data selector. We select which data should be in the output. But how it works, we would see in the next slide, and here is an internal design of a 4-to-1 multiplexer. You would ask, what is that, 4-to-1 or 8-to-1? 4-to-1 means that you have 4 inputs and you would get 1 output, and 8-to-1 multiplexer means you have 8 inputs and you would get 1 output. Now let's see the truth table for the multiplexer. As you can see, these are the selection inputs, S2, S1, S0, and Y is the output. Here the inputs are given as D, here I, it doesn't matter, they are the same things, the pictures are different. That's why one is D, one is I. Anyway, take them the same thing, right? Okay. So the logic is basic. The logic is quite simple. S2, S1 and S0 can be taken as a 3-bit digit. So, and we would convert it to the decimal number. So 000 accounts for 0 in the decimal equivalent, right? So the 0 would be routed to the output. 001 is 1 in decimal number, so the 1 is routed to the output. 010 is 2 and the 2 is routed to the output. 011 is 3 and the 3 is so I3 is routed to the output, and so on. As you can see, 111 accounts for 7 in decimal numbers, and I7 or D7 doesn't matter, is routed to the output. So basically I think you got the idea. By using the correct combination of S2, S1 and S0, using them as a data selector pins, we can route any of these 8 inputs to the output. That's the main purpose of multiplexer, to get one output among many other inputs. Now let's talk about the task itself. So the task is to create a 2-bit comparator using a multiplexer, and our condition is A should be greater or equal to B. In that case, we should indicate whether A is greater or equal to B or not. In my truth table, I assume that if this condition is met, so A is greater or equal to B, output should be 1, and vice versa, output should be 0. So, and here we have 4 inputs, as you can see, A2, A1, B2, B1, and A is represented by A2, A1, and B is represented by B2, B1. So A2 is the MSB of A, B2 is the MSB of B, and these are the LSBs of A and B. And one important fact is that these A2, A1, and B2 are connected to S2, S1, S0. So these 3 guys are the selecting inputs. So we would decide by looking at them which input is routed to the output, okay? So be careful about that. In our first case, as you can see, both of them are 0. So 0, 0, 0, 0, 0, 0. Because we have an additional B1, that's why we have a look the same case 2 times. But before analyzing this truth table, let's analyze the basic logic. So let's see what the numbers are and when the output should be 1 or 0. So A2, A1, it represents A. So 0, 0, A is 0. And B2, B1, 0, 0. So A is 0, B is 0, 0 is equal to 0, and our condition is met, so X is equal to 1. 0, 0, 0, 1. A is smaller than B, X is 0. 0, 0, 1, 0. A is smaller than B, X 0. 0, 0, 1, 1. A is smaller than B, X 0. 0, 1, 0, 0. This is 1 and this is 0. So I mean in decimal representation. So A is greater than B, so the output should be 1. 0, 1, 1, 0. 0, 1, 0, 1. So both of them are equal. Our condition is also met, so the output is also 1. 0, 1, 1, 0. This is 1 in decimal representation, and this is 2. So 1 is smaller than 2, that means output 0. 0, 1, 1, 1, 0. 1, 0, 0, 0. That one is greater than that one, so 1. 1, 0, 0, 1. That one is greater than that one. 1. 1, 0, 1, 0. They are equal. 1. 1, 0, 1, 1. This one is smaller. 0. 1, 1. 0, 0, this one is greater, 1, 1, 1, 0, 1, this one is greater, 1, 1, 1, 1, 0, this one is greater, 1, 1, 1, 1, 1, they are equal, so the output should be 1. Now, there is an interesting fact, there is an interesting point, better to say. Look, in this case, 0, 0, so this is the 1, this is output, 0, 0, 1, 1, 1, 1, 1, 1, 1. You can see in this case, whatever the B1 is, the output is in both cases 0. So, and the output, the routed input is D1. So D1 comes to output, and it's always 0. So we can connect D1 to 0, right? As I mentioned here. D1 is connected to 0. Here, output is always 1 in these cases, so it doesn't matter whether B1 is 0 or 1, it's always 1, and D2 is rooted to the output. So X is equal to D2 and it's equal to 1, so D2 should be connected to 1. The same here, so it doesn't matter what the B1 is. V3 is equal to X because of the selection inputs, and it's always equal to 0. I mean, these two cases, not always. So these 3 should be connected to 0, should be grounded. Here, 1 again. D4 should be connected to 1. D6 should be connected to 1. D7 should be connected to 1. But what about D0 and D5? Let's have a look at D0. 1, 0, 1, 0. So this is B inverse. This is B0, 1. So as you can see, when B1 is 0, the output is 1. When B1 is 1, the output is 0. So in both of these cases, output is equal to B inverse. So we can connect D0 to B inverse, and the same in D5. Look, 0 inverse 1, 1 inverse 0. So in both of those two cases, so the case 11 and 12, output is equal to inverse B1. So we also connect D5 to the inverse B1. And now I will show you the simulation. So I've done the simulation on Proteus 8.6, and I would also supply you with that X file in the description of this video. You can find them as a Drive link, Google Drive link, and you can download them if you have, of course, 8.6 Proteus. So this is the simulation of our circuit. As you can see, I connected the inputs as I've written before. So D0, D5 to B1 inverse. So B1 in B1, that's B1 comes here, and B1 is inverse as connected to D0 and what look D5. So we also implement these cases and we get such a circuit, and it works. You can see by running the file. And now let's see the realization of that on a breadboard. Now we would analyze our circuit. So this is my circuit I constructed on the breadboard, and I use the Arduino to supply voltage. It doesn't matter, you can use 5-volt battery. This is not the practical way. I mean, if you don't have an Arduino Nano, don't buy it, just use 5-volt battery. I used it at any rate. Maybe I would need any kind of edge triggering or not, but I didn't need. So let me explain that circuit a little bit more. So here we have a multiplexer. This is the NOT gate, so hex inverter. This is dip switch to give 4-bit input, and this is LED, and these guys are 1K resistors, and this one is 330 ohm resistor, and these are jumper wires, ground plus 5 volt, ground and plus 5 volt, and don't forget to connect these both sides together because they are default not connected. So in order to make our work easier, I draw something on paper so that we can analyze it together. So here A2 accounts for switch number 4. This is switch number 4. I'm not sure whether you can see or not. Switch number 3 accounts for A1, switch number 2 accounts for B2, and switch number 1 accounts for B1. It can be a little bit confusing, but take these numbers into account and you would understand. So in our first case, A2, A1, 1, 0, and B2, B1, 1, 0. So they are equal and the LED should blink, okay? And I'm connecting the power supply. Now the inputs are not like that, so I'm giving the inputs as in this case. But before that, I want to give a very important point. I want to mention it. So this side of the switch is grounded, and this side is the output of the switch. So if we turn on the switch, the output of the switch should be 1. The output of switch should be 0. So we short circuit it and get 0. So in order to get 0 for B1, which is the first part of the dip switch, I should short circuit it. So I turn it on. B2, which is the second one, is 1. So this is 1 because it's not turned on and it's not short circuited. I mean, the contacts are not closed and it's not short circuited, so it's 1. A1, it's the third. This one, it's 0, so I should put 0 to that. 0. And A2 should be 1. Now it's 0, I make it 1. You saw? The LED is on, that means these two numbers are equal to each other, or A1 is greater than B2. In our case, they are equal, but it's also the case that A is greater than B. Now let's consider the second case. Here, third and fourth are short-circuited. Now third and fourth short-circuit. Fourth is short-circuit, but the third not. I short-circuited. And B2 is 1, yeah. And B1 is 0, 0. So the LED is off. That means A1 is not greater or equal to B. I mean, A is not greater or equal to B. So the second case also met. Correct? Correct. Now, let's short circuit all of them. That means all of them are equal to 0. 0 is equal to 0, so the LED should be on. And now the last case, A is greater than B. How we can get it? This is 1. Sorry for my bad handwriting. So 1, 1, 3 and 4. Both of them should be closed. Should be opened. I opened the circuit in that part. And B2, 1, B2, 1, and B1, 0. You see, the LED is on. So that means A is greater or equal than B, but in our case, it's greater, the LED is on. That means our circuit works properly, works 100% correctly. I don't analyze all the cases because that would make the video longer, but I've analyzed it myself and it worked, and I showed you 4 possible cases and all of them worked properly. So our circuit works quite well. If you have any questions about the circuit, you can write it in the description below. Now, let's see our additional task. So another application of multiplexer. It's called parity generator. What's a parity generator? In digital electronics, errors can happen, and we should define them. We should indicate whether there is an error or not. To do that, they add a parity bit to the data. So in our case, parity bit is A0, and these are again the selection inputs of the multiplexer. So if there is a problem, this is the this is the data that we send, and this is the parity bits that we add to be sure whether there is a problem, there is an error or not. So when the number of ones in the data, in the whole data, is even, that's called even parity. If it's odd, in that case, it's called odd parity. We assume that in our case, when we have the even parity, the output should be 0, and when we had odd parity, the output should be 1. But it doesn't matter. You can take in even parity, the output should be 1, and vice versa in odd parity. The truth table would be changed, but your circuit would work 100%, okay? So don't worry about that. Do whatever you want. I mean, just change them, not whatever you want. Okay. So let's analyze again our truth table as we've done before. So here you can see 0, 0, 0. So 0 is an even number and the number of ones is even. So as in our condition, output should be 0. Here, the number of ones in the data for big data is odd, so output should be 1. Odd output should be 1. Even output should be 0. Odd output should be 1. Even output should be 0. Even output should be 0. Odd output should be 1. Oh my god, that's the tongue twister output, then should be. Anyway, so let's see, okay. Odd output should be 1. And even output should be 0. Even output is 0. Odd output is 1. Even output is 0. Odd output is 1. Odd output is 1, and even output is 0. Now we use the same tact as we used before. We analyze the output, we have a better look to the analogy between the output and A0, because this is the parity bit and it would have some influence on the output. So, as you can see, D0 is the same as A0. I mean, when D0 is routed to the output, in these two cases, it doesn't matter. I can't say it doesn't matter, but whatever the A0 is, output is the same with it. So we connect D0 to A0. Another such a case is D3. Look, same. D5, 0, 0, 1, 1, same. D6, 0, 0, 1, 1, same. And when it is equal to A0 inverse, let's see, D1, so this is A inverse, A0 inverse, and these are our outputs. So look, equal D2, equal D4, equal D7, equal. So we connected these guys to A0 inverse and these guys to A0. And let's see it on a simulation, you would better understand it. Look, I did the connections as I mentioned here. And when this that means the output is 0, so the data has even parity, and this shows the parity bit. And now let's see the video version, I mean the realization of that circuit on a breadboard. So again we have the circuit, I mean the realization of our project parity generator. So you can see the dip switch numbers 1, 2, 3, 4 and A0, A1, A2 and A3. So the first case 0, 0, 1, 0. The number of ones are odd, and let's implement it on our circuit. Now all of them are 1. So we need 0, 0, 1, 0, 0, 0, 1 and 0. So the LED is off, that means the output is odd, I mean there are odd number of ones, and when we make the last digit 1, let's see what happens. the LED is on. That means we have even number of ones in the input. So this is how parity generator works. Now, our last construction, our last creation. BCD invalid code detector. You would get confused. What's that? BCD. BCD is the short form for binary coded decimal. Binary coded decimal is mainly used for 7-segment devices to represent the inputs in 7 segments. I mean, in electronic clocks work like that. So in BCD, every one digit should be represented in 4 bits binary numbers. So 1 in BCD is 0, 0, 0, 1, and 46 in BCD. Look, 4 is separately converted to BCD and 6 is separately converted to BCD. Better to say to binary numbers. So 4, 0, 1, 0, 0 in binary and 6, 0, 1, 1, 0. And BCD is used only to encode from 9 to 6 because in clocks we don't need 100, right? So there are 7 segments and we can get any number by using 1, 1, 0. We don't need to get directly the 110, okay? So there are 6 invalid BCD code words: 1010, 1011, 1100, 1101, 1110, and 1111. So this is 10, 11, 12, 13, 14, and 15 because 4 bits means we can go up to 15. So the task is actually basic if you understand up to this point. We should indicate if the inputs are one of those 6 guys. And I assume that if the input is one of these guys, the output should be 1, and in other cases, better to say, the output should be 0. And I made my truth table. So you can feel the logic here. It doesn't matter the truth table should be like that or like that. You create it yourself. You make the logic yourself. You assume whether it should be 0 or 1. It doesn't matter what has been written in the book. Okay. The perfect side of the multiplexers is that you can get any kind of Boolean expression by assuming the output yourself. So the structure of truth table is a little bit confusing here because the cases were different from the previous 2 projects, but anyway, you would understand it, I suppose. So our data is BCD code is 0, 0, 0, 0. That is a valid BCD code, so output should be 0. 1, 0, 0, output 1, output 0. Sorry, 0, 0, 0, 1. You see, these are normal cases. They are valid BCD codes. But what is that red little guy? This is 1, yeah? That means this is an invalid code. Why? Let's see. 1, 0, 1, 0. Oh my god. That is here. That's a bad guy. And we put the output 1. 0, 0, 1, 1. Oh, it's okay. And again a red guy. A red 1. 1, 0, 1, 1. You see? This is an invalid code, so we indicate it. And it goes up to the end, right, like that. And now let's analyze the truth table again. In these 2 cases, look at the outputs. They are always 0, so the 0 should be 0. Whatever the inputs, I mean, whatever the B3 is, the 0 is equal to 0. Again, the 1 is equal to 0. And now here, 0, 1. Let's find what's that. Look, B3 is equal to 0, 1. You know why we always take 3 inputs together? I mean 3 data together and 1 separately. Because the 8-to-1 multiplexer has 3 selection pins and another pin we add ourselves to the input somehow to manage the output. that's a very good tact. So 0 0 1 1, that means D2, these both cases root D2 to the output, is equal to B3, 0 0 1 1. So D2 should be connected to B3. Again, 0 0 1 1, D3 should be connected to B3. 0 0 1 1, D4 B3, D5 B3, D6 B3, D7 B3. Look, you can analyze it yourself, they are correct. And again, we did that connections on the simulation to see whether it works or not. We have done it correctly or not, and let's see how our connections are. So as you can see, they are the same as I mentioned before. The connections are like that, and code validity means that when the output is 1, that means there is a problem. So let's and now let's see the realization of this project on the breadboard. Now let's see how our BCD invalid code detector circuit works. So I have 4 cases. The first case is 0001, which is a valid, so the LED should not get turned on. So 0001, the LED is off. So that's an invalid case. 1 0 and 1 and 0. So the LED is on. That means such a BCD code doesn't exist, and this is invalid. So the next one, 0011, 0 0 1 and 1, so LED is off, correct, valid. And 111, 0 1 1 1 0, the LED is on. That means the case is invalid, such a BCD code doesn't exist, the circuit works properly. Now guys, as a conclusion of this project, I learned some kind of things and I would like to share it with you. Tips working with ICs. What's IC? IC is integrated circuit. So these small gates, pressed together, used in digital electronics, called integrated circuits. They are so small actually. All the computers are made of transistors and they are quite small, in nano size. So actually there are a lot of tips working with ICs. I would like to mention 2 of them. The first one is the datasheet of the elements should be checked in order to be able to use them properly and do the connections correctly. And that's right, if you do the connections in a wrong way, it could burn your device. It could lead some kind of errors on your output and you would not be able to detect it, okay? So first of all, if you have a project, if you have an IC, not IC, whatever you have, if there is a datasheet on the internet, you can find it, you should check it 100%, okay? And I would attach the datasheet of the multiplexers that I've used in the description of this video, so you can check it and see how to use it actually, because I also used that datasheet to do my connections actually. Because without them you can't understand anything. ICs are small chips and there is only the code for the IC on it. There is not the VCC ground indicated on the ICs. You should check the datasheet. Okay. Second tips is the inputs of the logic elements. So better to say, integrated circuits should not be kept open. This sentence can be confusing a little bit, but I would explain it. So you can think that if the input is 0, I would say kept it open, not connected to any point, but no, this would lead some kind of errors. I checked myself during my projects and I checked 2 cases. I had a LED on the output of an integrated circuit, and in one case I connected ground to 0, also 0 to ground, and when there is 1 in the input I connected to the 5 volt, and I saw that the LED works without problem and it's quite bright. And in another case, I checked, let's see what happens. What happens when we don't connect the zero input to ground? It's always zero. Yeah, we can do that. So there's no voltage means zero. But I saw that the link's brightness went lower, so it's how to say it the dimness of it get lowered, and that helped me to understand that it's quite important to connect 0 to ground and 5 volt to, I mean 1 to 5 volt. In another case it would lead to any kind of problem. So keep in mind, okay? Don't keep them opened. Connect them. If there is 0, connect them to the ground. I hope you understood it. And as a final, I would like to thank you all guys for watching. This was the topic about digital electronics and mainly about multiplexers. I hope you understood. I hope I could explain everything correctly, clearly. If you have any questions, write in the comments below, please. And if you have any kind of criticism, I would like to get it. Maybe my accent, my speech would be some kind of itching, but I'm not a native speaker. That's possible. And again, this video is presented by Farid Hamidov, so me. And as every YouTuber, I also would like, better to say, I should mention that please do not forget to subscribe.